Hello, this is Lovedeep Gandhara, and I'll be presenting our study, Differentially Private Survival Function Estimation. As we know, Kaplan-Meier's method is one of the most often used methods for the survival function estimation in clinical studies. And given the nature of underlying data used for estimation, that is, the patient-level data, it is of paramount interest to protect the privacy of the contributing users. In order to do so, we propose a differentially private version of the Kaplan-Meier estimator. Our method, being simple and straightforward, can be easily extended to estimate many other related quantities, such as differentially private hypothesis tests to compare two survival distributions and differentially private confidence intervals. In summary, we start with a partial matrix M that has number at risk for the first time point and the number of events for every other time point. Then, using that partial matrix, we add noise to it from the Laplace distribution with a sensitivity S and our privacy parameter epsilon. Now the M prime, that is the noisier version of M, is differentially private. Then using M prime, we complete the number at risk, which is done in a similar way as we would do if we would have non-noisy data. Then using the noisy number of events and the noisy number at risk, we estimate our survival function, which is now differentially private. The sensitivity for our scenario for the partial matrix M is 2 because we only have the data for the very first time point for number at risk and for every time point for number of events. So adding or removing a single individual can only change the counts by at most 2, that is, being either in at risk for the first time point or having an event. The differential privacy of our algorithm 1 can be similarly proved using the sensitivity and the fact that we only use noisy terms for our function estimation. And as we have talked briefly before, our method can be easily extended to estimate the confidence intervals around the survival function in a differentially private way and the hypothesis test. And our method can be easily extended to estimate the competing risk cumulative incidence and the Nelson-Allen's estimate of the hazard function in a differentially private way. For the results, we use 9 real-world data sets, and we can see that our method provides good utility. And as expected, the utility gets worse when the noise level increases for tight privacy or when the dataset size gets smaller. And we observe similar trends when looking at the estimates of the median survival along with the confidence intervals. For the complete set of results, please have a look at our paper. In the end, we would like to acknowledge the support from NSERC in the form of a CGSD award and a discovery grant. Thank you very much.